So the final long speaker of this session is going to be Michael Snyder. Mike is the department chair of genetics here at Stanford. And within Wutsai Performance, he is a member of the moonshot on the molecular athlete. The floor is yours.
Thank you very much. It's great to be here. So we also make measurements, and in our case, it's very, very deep molecular and physiological measurements with the goal of trying to actually improve health as well as performance. And I have lots of conflicts. You can see them all there, and you can not trust anything I'm about to tell you. I do think the tools and technologies we're building, by the way, are quite powerful, and we're actually set up many, many collaborations now across the Alliance with some of what I'm going to tell you. So a number of years ago, we set up what we call deep omics profiling, where we sequence people's genomes along with making deep molecular measurements around people, mostly out of blood and urine. So we'll look at their RNA, their proteins, their metabolites, their lipids, as many molecules as possible out of the blood. We also follow the microbiome. This is on top of deep clinical testing and other kinds of measurements as well. So one aspect of this is to take very, very deep molecular, as they say, profiles, and the other aspect is to do it longitudinally, follow people over time so that we can see what it means to be healthy and how does that shift and what people's healthy profiles look like. And it turns out everyone's quite unique in their profiling. That's not surprising, but they actually are quite different in the sense that a sick you is closer to a healthy you than the person sitting next to you. So meaning that our differences, our individual differences are quite large, and we pull this out with these kinds of measurements. So from these deep profiles, we started this on a smallest group, 109 people. Just from the first 3.5 years, we actually had 49 major health discoveries, things all found pre-symptomatically. So by doing these deep profiles, if you will, we can see things at a level people haven't done before. So we like to think of this as if your health is a 1,000-piece jigsaw puzzle, we're trying to find 600 or 800 pieces versus, say, the 6 pieces you currently get when you go to a physician's office today. So try to see these things deeply. And some of these turned out to be a big deal. We caught some with early lymphoma, some pre-cancers, 2 people with serious heart issues, so on and so forth. Again, all found pre-symptomatically. And with the combination of these different technologies, no one technology found this. Again, it was multiple technologies, often together, that would reveal something was off. So that's actually generally what we do. We also do this during people's performance, meaning when people have done an acute bout of exercise, we can see how their molecular profiles shift and follow all their biochemical pathways that shift. That's turned out to be quite interesting. Now, another aspect very relevant to everything you're hearing at this meeting is that we're trying to do remote sensing as well. You've heard about wearables. We spent a lot of time on this. Actually started when these were mostly viewed as fitness trackers, but we actually use them as deep physiological monitors. And we also do something with microsampling. I know what that sounds like, but this one actually works, where we collect small blood samples. So with the wearables, what we're doing is actually basically putting devices on people. You may notice I have 4 of them. My hearing aids, they are for hearing, but they also are sensors as well. So we're using all kinds of different sensors to follow people's physiology and activity at levels that haven't really been done before. And we showed early on that you can actually tell when people are getting sick before they realize it. We originally found this when we detected Lyme disease, it turns out in me, pre-symptomatically. And then later showed we could tell respiratory viral infections, again, pre-symptomatically. And resting heart rate turns out to be one of the major parameters for this. It turns out that, you tend to measure these things with temperature, which is really a 300-year-old concept. It doesn't work that well for COVID if you think about it, right? Because half the people don't get a fever. So actually it turns out resting heart rate is a very, very sensitive measure of physiology. And so obviously when the pandemic came, we scaled this up quite rapidly and showed we could detect COVID 80% of the time, retrospectively initially. And the median was 4 days prior. I think I'll point here, I'm told this will work. Never mind. This will basically will detect COVID pre-symptomatically 80% of the time, and the median is 4 days prior to symptom onset. COVID has a long pre-symptomatic period. That's our very first case there. The top plot is actually resting heart rate. And you can see there's a standard deviation plot. That person's resting heart rate jumped up. The red is when their symptoms first appeared. The purple day 48 is a diagnosis day, but the resting heart rate jumped up 9.5 days prior to symptom onset. You can't miss that signal. It's very, very prominent. So we gone on to build real-time detection systems, and I think this is quite powerful for the themes talked about at this meeting, where we can actually follow people based on their circadian patterns, look for a shift, anomalous shifts from their baseline, and actually, again, tell respiratory viral infections, case COVID, same number, 80% of the time. And we have this real-time alerting system. You can all sign up for the study, by the way. You either get green days, means things look like your normal baseline, or red day means you've had a certain number of standard deviation shifts in magnitude or duration over your baseline, and get red alerts. And it does work. It worked on me, where it's actually more sensitive than an antigen test, actually. It's not as specific because other things can trigger these alerts. It's not specific for COVID. Workplace stress is #1 red alert triggers. But actually, you can quantify all this and capture that. I know we'll ultimately, with more data, tell the difference between workplace stress and a respiratory viral infection. The data's limited. That sharing theme you heard earlier, that resonates well with us. Most people don't share their data. It's not the people's fault. It's the scientists. They're terrible at sharing data. So we've got to change that culture. We do a lot with continuous glucose monitors. And I won't get into this a lot, but we put these on normal people, pre-diabetic. And what we discovered is that a lot of people are thought to be pretty normal actually spike just as bad as diabetics. They have very poor glucose control. And you may know, so this is what these glucose monitors look like on the left. Different people spike to different foods. Some people spike to bananas, others to pasta, some people to white bread, some to brown bread. And it very much depends on the person. Your microbiome is partly responsible for that, but there's a lot of other factors we don't know. So just by example, this is from Aaron Siegel's work, the top right. That's a person who spikes to banana, but not to a cookie. Probably the only person on the planet who doesn't spike to a cookie. The person on the bottom is more normal, spikes to a cookie, but not a banana. And again, it's all very personal. I guarantee a lot of you are spikers who don't know it. Okay, 9 out of 10 pre-diabetics don't know it, by the way. All right, so we've done a lot. We've spent 6 years trying to do this remote microsampling, working on technologies where we could get stable analytes. And so, as I say, what you can do is do these tiny little blood pricks in these devices. These days we use a separate device. And the idea is you would FedEx it. We'd process it in the lab and do these deep omics profiles. It could measure about 2,200 analytes from these 10 microliters of a blood drop, actually 20 microliters. Okay, and a lot of these are actually quite interesting and important molecules relevant to the exercise and physiology field. It turns out we've showed stability of the various analytes and then went on to do some fun experiments. So this is a case where we had 32 people drink this Ensure shake. You've all probably heard of it, seen it in the grocery stores. Doesn't taste very good. We sampled them before they drink the shake and then at 4 time points afterwards. And then we follow all these molecules. And the cool result is everybody's different. So just take a look. Each box is a different person. See that brown box where going down, these are just 3 carbohydrates. That person's carbs totally plummet. You go over a little bit, there's a 3 over, light blue, that person's carbs skyrocket after drinking the shake. So on and so forth. You'll see different people going up and down depending on their individualized response, and we can measure this. And at the bottom, it turns out there are 5 categories of people, but some of the coolest results are the one I'll actually drift over here. Looking over here, we can follow inflammatory markers. This person drinking the marker, their inflammatory markers go down. It's anti-inflammatory to them. To this person, it goes up. Same with group 1 over there. So the same people, or different people drinking the same shake have very, very different responses. And obviously we can measure this then during athletic performance, we think as well, with these kinds of technologies. In fact, we're actually sampling someone's about to run a marathon. We're going to sample them through the marathon. Should be a little tricky, giving droplets while they go. But anyway, they'll pull it off, I'm sure. Just to show you they can pull it off, here's one person who gave 98 samples over 7 days, basically every hour, plus or minus. And we did the deep omics profile, and we compared it with the wearables. We can actually follow time-shifted correlations, if you will, which gives an idea what events might be causative versus reactive to certain conditions. So for example, your heart rate goes up after steps, and we can quantify that, show it's about a minute lag. And we can do this for everything, for glucose, all kinds of things. We can measure with the wearables and molecular measurements. And the upshot of all this is we find thousands and thousands of correlations between your physiological measurements and your molecular measurements. Some of these turn out to be pretty cool. Things like alpha-synuclein, which is involved in Parkinson's. We can see when that spikes relative to glucose. All kinds of glucose control measurements, inflammation markers, all at a personal level, all for the individual. Okay, so we have a dashboard to pull all the data in. You can show wearables, clinical, omics data, all put together for your own personal use. We have a team that's done this. I won't have time to go through it, but we have an amazing wearable and microsampling team. And with that, I'll close.